series. And Ilaria Kaitso and Jan van Roystel are running the club. I usually do the invitations, but they do all the hard work after that. And so today, it's a great pleasure to have both a distinguished UV astronomer and also my friend Mike Shull giving us a lecture on UV astronomy, many applications of your many projects in UV astronomy, science project, but also he's on the COS, the Cosmic Origin Spectrograph team, and that's the most sensitive UV spectrometer we have, a far UV spectrometer. So we'll get to hear the latest from that. Um, so I wanted to. Mike has a very simple career in that sense. He did his undergrad at Caltech, um, and then went to Princeton um, and did what used to be a standard Princeton PhD. Regrettably, it's no longer the thing where all Princeton PhDs we finished in 4 years, which I really, really like. Um, anyway, and then went to Berkeley for a year, worked with Chris McKee and others. And after that, University of Colorado at Boulder, and been there ever since. Okay, it's a rather simple trajectory. He's now officially emeritus and commutes between North Carolina, where he has a home, and Boulder, depending on, I guess, the season. Presumably, winters in Boulder and summers in North Carolina. No, I mean the other way. Okay, but I wanted to share something with you, which is uh, there's a really nice site here. Um, okay, which I actually enjoy reading because it also tells, and it's part of it my not so much a hobby. Um, in my mind, there are many scientists who are talented, meaning they know differential equations, they can reduce data, they know all that sort of what I call technical stuff. But um, some of them go and achieve great stuff, and many just plod along, you know. I always wondered, why is it that given the initial conditions which are the same, different people do achieve differently? And I think the answer has to, in my opinion, is selection of problems. Okay, I think great scientists know how to select problems that are both important and solvable in a certain time. So I always enjoy reading about people sort of like an oral history, and there's a bit of that here I found on this site. Tells me about how Mike grew up in a family. His father was a pilot, learned a lot about, he knew a lot about the stars. I know they're basically the asterisms, the constellations. Then he decided he'll do physics, went to Caltech, then to Princeton, where he realized that astrophysics is much more interesting than physics. So already you're showing signs of good choice in his life. And even within that, though he started working in globular clusters, he showed even better choice by working on ISM. I mean, the two best fields in astronomy are ISM and pulsars or something like that. And sort of then really branched out into many aspects of that. This is a great site. I actually discovered accidentally, but it has interesting kind of oral histories of like Mark Harwood, Judy Pfeiffer, George Reiki, John Mather, many recognizable names. And I actually found a nice weekend reading, and I recommend young students. History is important not because of anything else. It's just it gives you strategies for the future, and personal histories are important because it gives strategies for your future. Okay, with that sort of a little philosophical detour, off to Mike.
Okay, thanks for that. That site was actually something Don York and his colleagues at Chicago put together. And who knows how they picked us, but it was a random group. Let me share the screen so I can get started, and I hope this works. Is that coming through okay?
Yes.
Yeah.
Okay, good. So this is going to be sort of a personal selection of topics that were enabled by the launch of or installation of the Cosmic Origins Spectrograph on Hubble. I wanted to thank, of course, a number of CU collaborators. Jim Green, who actually might be online here, I gave him the Zoom address. Jim is the PI of COS. He was the person that led the team and building of it. And then a lot of science colleagues, most recently Charles Danforth, John Stockey, and a number of grad students and undergrads. At the bottom is a wiki page, which was written by the team. So I recommend it if you want to read succinctly about what COS is. So this is a long time ago now, coming up on, well, I guess it's 12 years ago. In May 2009, the last shuttle mission to the Hubble installed 2 new instruments, and they fixed up a lot of other things, the gyros, batteries, and infrastructure. And amazingly, 12 years later, both of these new instruments are still working just fine. So there is one of the astronauts putting in the COS into the aft bay, so you can see where it goes. And here is somewhat of a busy diagram. You can read about this in Jim Green's paper with the science team. And there's another paper that went along with it by Steve Osterman about online performance. So we were proposing the far UV, and we won, but the review team said, well, we would like to have a near ultraviolet channel too. So if this cursor works, this is the rather complicated near UV channel. And down here is the more simple far UV channel. And the key to the high throughput, which I'll come to, is that in the ultraviolet, you want to avoid or minimize the number of bounces off mirrors because the reflectivity is just not that high. So if you do what's done in the optical and you really have great optics, it often involves many bounces. Can't do that in the UV. So the miracle of COS that the team came up with, and Jim Green's design made happen, is that this mirror down here that does the first correction of the aberrated optics of the Hubble mirror also has the gratings in it. And so with one bounce, you take it back here and back to the detectors, which for the far UV are XDL, extended delay line detectors. The near UV is a little more complicated, and also because it used the MAMA detectors that were flight tested before on a previous spectrograph on Hubble. It was limited in a way that I'll come to, limited in that ended up to cover the near UV band, there were actually 3 different gratings. So that's the gist of it. Now on the bottom, we're going to talk about 3 gratings. So this follows the nomenclature of the Hubble. The letter M stands for moderate resolution, and G stands for grating. The letter L is low resolution, and the numbers here are the central wavelengths in nanometers. So this is 1300 angstroms, far UV, 1600 angstroms, still far UV, but a little bit longer. And there's an overlap, a little bit of an overlap. There's also some gaps in the detectors, but you can fix that by a proper choice of placings. And then the G140L, centered at 1400 angstroms, goes all the way out actually to almost 2200 angstroms. So over here on the right, you see what we call the effective area. That's the throughput in square centimeters after all the bounces and after you take into account the detector efficiency. So you start out with a 2.4 meter mirror, which is small by optical standards, but it was big by space UV standards. And after all the bounces and such are done, you end up with a peak of a few thousand, maybe 2000 square centimeters. 0.2 square meters in these moderate resolution. So this is the 130M in blue, and then in magenta, the 160M. The G140L is a little bit lower throughput, but it covers a lot more wavelength territory. So in one setting at low resolution, you can go all the way from 1,000 angstroms at not much throughput up through the standard far UV, 1200, 14, 1600, all the way out to about 2100. So if you compare that to the previous spectrograph, which is still on board and still used a lot, STIS, Space Telescope Imaging Spectrograph, this is the E, stands for Shull spectrograph, 140M, moderate resolution. And you can see it's a lot lower throughput. It peaks at about 200 square centimeters. So this next slide shows on a non-logarithmic scale, just to really show how good the throughput is on cost, the 130M and 160M gratings. This was done before the on orbit, so this was estimated in dotted lines, but that's about correct. And you can see at its peak, 1200, 1300, 1400 angstroms, it's 10 to 20 times higher than STIS down here. And then here's the 140L. Just for those of you who are a little bit older and may remember the Far Ultraviolet Spectroscopic Explorer FUSE, Colorado and Johns Hopkins and Berkeley built that, and it was launched back in the 90s and lasted a good long time. You can see that it was much lower throughput, but also pretty good resolution. But the key for FUSE was it went all the way down to the Lyman limit, 900 angstroms, 912 angstroms. And that is our hope, our dream, to recover that capability. Maybe we'll get there with the next mission. I should also mention this little magenta piece that I drew in. This is called the G130M Super Blue. You can alter the setting of the gratings depending on where you want to emphasize and to move the gaps around between the gratings. So this Super Blue, which is now being used a lot if you want to get down below 1150 angstroms, this takes you down to about 1050 angstroms with a little bit reduced resolution in kilometers a second, about 25 kilometers a second. Up here in the far UV, the resolution is about 17 kilometers a second in its moderate form. Okay, I'm not going to dwell on this. I just put this in here. It's on the wiki page. This shows all the gratings and the different coverages. But the moderate resolution that I'll talk a lot about are the FUV gratings, G130M, G160M. And now just a little bit about the near UV, which is on the lower part of the chart here. In order to cover the near UV, which was added on to the original proposal, the design team came up with a way to do that with stripes and 3 different gratings to cover the wavelengths all the way out to 3200 angstroms. So that is the G185M, 225M, 285M. There's also a low resolution grating, G230L, centered at 2300 angstroms. And so if you want to do survey mode at low resolution and you're not too concerned with resolving absorption lines and velocity resolution of emission lines and all that, then these are for you, 140L, 230L. If you want to get good resolution, moderate resolution, 17, 20 to 20 kilometers a second, you use the M gratings. Okay, so just a little bit of pedagogy. Shri said to spend the first part of the talk familiarizing you with why the UV is an important area of multi-wavelength astronomy. One reason, which we used all the way back in the FUSE proposal, was this figure. So I've modified it a bit. It was originally constructed by Ed Jenkins, who took the line list of strong resonance lines of atoms and molecules that you could see in the far and near ultraviolet and optical. And he made a table with histograms of where these resonance lines lie. Now, there are a few in the optical, and this is where a lot of early work in the interstellar medium was done. plus the 21 centimeter line of hydrogen in the radio. But the early work in the optical used sodium-1 and calcium-2, potassium-1, and a few molecules, CH, CH+, and so on. But if you want to get the strongest, most sensitive lines of atoms and molecules, the UV is a good place to look. So here is the carbon-4 doublet at about 8 eV, 1549 angstroms, wavelength scales along the top here. So carbon-4 is a real workhorse of finding ionized, fairly hot gas. Lyman alpha is right here at 10.2 electron volts. And of course, 21 centimeter opened up the interstellar medium back after World War II, when radio astronomy really took over. But this Lyman alpha line, being the resonance line, is about 1 million times more sensitive in terms of what column density you can detect. So Lyman alpha is a workhorse of UV astronomy, along with, for the heavy elements, carbon-4. And over here, I'm going to highlight oxygen-6, which is sensitive to gas at 10 to the 5th to 10 to the 6th Kelvin. It's a doublet also, like carbon-4, at 1032 and 1038 angstroms. But there are many, many other lines of heavy elements: carbon, nitrogen, oxygen, silicon, sulfur, iron, nickel, etc. And this blue band shows that they just peak. It looks like they peak at 13.6 eV. They actually continue, a number of them continue on into the EUV, the extreme ultraviolet. And the next slide, we'll talk about those. Now, the molecules that you can see in the UV, there are a number of them here in this little red band, and over here and here. These are molecules of molecular hydrogen and deuterium, deuterated version of molecular hydrogen, HD, right here. And of course, carbon monoxide, which also has a lot of UV lines. And there are other diatomic molecules that have resonance transitions with vibrational and rotational modifications, but the strong electronic transitions are also in this band. So we made this case that if you want to study the abundances of atoms and ions and molecules, you want to look in the optical, to be sure, but also into the Hubble band and into the far ultraviolet, down to as far as you can go, which practically nearby in the interstellar medium is 912 angstroms. That's 13.6 electron volts. That's where this plot that Ed Jenkins put together stops. And that's because that's 1 Rydberg. That's the energy it takes to ionize hydrogen. So the adage that we all were taught was, well, beyond 1 Rydberg, it's very hard to observe because the hydrogen in the interstellar medium absorbs it. So it should be black. Well, not quite. And Stu Boyer and Jim Green and Chris Martin and many others that came out of Berkeley proved that the EUV can still be observed locally out to 100 or 200 parsecs. You have to go down to about 100 or 200 angstroms to do it. A few nearby stars you can see beyond the Lyman limit, but it's hard. But we're in an expanding universe. So the next slide shows what we have now proved with COS through the magic of the redshift of quasars and some Seyfert galaxies and some regular galaxies. You can observe in their rest frame well below the Lyman limit. And the thing that gets in the way, again, is molecular and interstellar hydrogen and the Lyman alpha forest of intergalactic hydrogen. But because of the redshift, if you can make it out of the galaxy or make it out of the quasar, an EUV photon will come right on through and we can detect it. So this is a composite spectrum, and I'll be coming back to that later in the talk, taken with the G130M moderate resolution spectrograph. We did that for a reason. We've come back with 140L, but if you want to resolve all this Lyman alpha forest, and that's what this black spectrum is, you need to have moderate resolution to get in between the hydrogen lines, the Lyman alpha lines. Now on top of that, this red spectrum shows the underlying spectrum of the quasar after you subtract out the Lyman alpha forest. And it's, as you can see, just full of these EUV, extreme ultraviolet lines, below 912 angstroms. So here are a couple. Oxygen 2 and oxygen 3 have lines at 833 angstroms. There's a neon 8 doublet at 770 and 780. Here's a list over here if you want to see where they are. The neon 8 line is also being seen a lot in quasars. And then there's many, many more. They're mostly high ions of oxygen and nitrogen. Here's O5, O4, neon 5, O4. So this red line shows the broad emission lines of the quasar. So later in the talk, when I come back to the science that we've done with COS, I'm going to emphasize what you learn, not only from these emission lines, but from this underlying continuum, which is probably non-thermal. It's probably a mixture of synchrotron radiation from accelerated particles in the quasar, and maybe also from thermal radiation from the accretion disk. It's probably a mixture of both. Now, the two bits of science I'll point out that I'll come back to later are these cyan boxes. At 912 angstroms, that's 1 Rydberg, 13.6 electron volts. That's where most models of accretion disks said, well, there should be a strong edge, just like in stars. When you have hydrogen in the atmosphere of a star, you get an edge. So O stars show edges, but there was no edge at all seen. And similarly, if you had any neutral helium in the atmosphere of the quasar, either in the broadline region or the accretion disk, you should have seen a strong edge right here. Nothing. So I'm going to go through now, after this preliminary pedagogy, go through 3 areas of science that were both in the design mission for COS, but also we actually did it. Well, not just we, people now all over the world are using cosmic origin spectrograph to do their science. Now, in the interest of time, I'm leaving off a number of important things that people have done, including white dwarfs and planetary nebula and supernova, planets, extrasolar planets, and solar system planets. I'm going to start first and talk about massive stars, which of course are very strong emitters of UV light, and starburst galaxies are full of them. And then I'm going to shift to one of my favorite topics for the last decade or two, the intergalactic medium and circumgalactic medium, gas in between the galaxies and out in the halos of galaxies. And there's 3 applications I'll talk about: counting baryons, measuring the ionizing background in the UV, and then looking at this CGM, the circumgalactic medium, that was part of the work that COS science team started, but it really took off when one of my former students, Jason Tummelson, and his colleagues found a bunch of galaxies with the Sloan survey and probed them with oxygen 6. And then finally, something I've been working on with my students a lot, because of this miracle of the redshift, probing the rest frame spectra and emission lines of quasars. So let me jump in with several slides on hot stars. There's a whole science project, legacy project going on with Hubble called Ulysses. So if you Google Ulysses or the legacy project in UV, you'll find a lot of papers led by Klaus Leiter and others, mostly in Europe, but some in the US, dealing with hot stars in the Milky Way and the Magellanic Cloud. And the Magellanic Cloud is where they put a lot of emphasis because it's a starburst galaxy, very nearby. So this plot is going to focus on starburst galaxies, much like this superstar cluster around the Tarantula Nebula called 30 Doradus. So over here is to locate where it is. But you can see there are many star forming sites in this beautiful image in the H alpha filter that David Mallon put together. Of course, supernova 1987A was right down here. But many other stars are just getting ready to explode, I'm sure. We can just wait long enough. Yes.
I don't think I can see, I've not been seeing your cursor. That's okay, just letting you know.
Okay, thank you. I will use words. So the 30 Doradus at the very center of it, in the early days of IUE, the UV astronomers at Wisconsin, including Blair Savage and Joe Casanelli, wrote some very nice nature papers thinking that they had found right at the center of this R136A cluster, a massive star, supermassive star of several thousand solar masses and a very powerful wind seen in UV lines. Well, it turned out through the miracle of, another miracle of interferometry and speckle interferometry in particular, that single object broke up into many 100 and 150 solar mass stars. And you can see that here. Okay, so here is a spectrum. This was taken by STIS, and I'm showing you the G140L. What you can see with low resolution, 1.8 angstrom resolution. And what you see, and what you get from even at low resolution, are P Cygni lines indicative of outflows. So where the green box is points to the P Cygni profile of carbon-4. This is the 1549 angstrom doublet. And it's a doublet split by 3 angstroms. And you can see hints of the splitting if you look carefully. But there's an absorption component, blueward, of 1549, and then there's an emission component, redward. And so it's emission in redward, that's the outflowing wind. And then when you look blueward in absorption toward the photosphere of the star, you see the absorption line. Now, what you can't see very well are the interstellar lines. They're there, but at low resolution, except for the really strong ones, you don't pick them up. And I've labeled the strong ones of silicon-2 and oxygen-1. There's also down near Lyman alpha, the nitrogen-5 doublet at 1238 angstroms. That's also in P Cygni emission and absorption, but it gets clobbered by Lyman alpha. So with this kind of thing in mind, Koss and STIS have gone on to look for starburst galaxies. There's a paper by that team, James et al., that I call to your attention. These are UV images, and then they've overlaid the circle of the aperture, which is 2.5 arc seconds on COS. And so you can see when these galaxies get pretty far away, you're not able to zero in like you can in the LMC and zero in on individual stars. You get the whole cluster. So these are some famous, quote, nearby starburst galaxies. 1Zwicky-18 at the top left is a very famous one with about 1/40th of the solar metallicity. These are important both for their own right and for hot stars, but also because we think that galaxies like this may have reionized the universe back at redshift 6, 7, 8, or even earlier. That's for several reasons. First, these are probably the garden variety galaxy that was forming back then, just out of the dark matter cosmology lambda CDM model, but also because the Lyman alpha and Lyman continuum photons can get out. They have fairly low gravitational potentials and escape velocities. And so the gas can get blown out and open up clear channels for the Lyman continuum to escape. So I'm going to now, of these 9 galaxies, show you some of these star clusters observed with the moderate resolution G130M spectrograph on Koss. Again, the same paper came out a few years ago. And of course, you see that Lyman alpha, where my red arrow is the most prominent feature. The broader it is, the more hydrogen it is, there is in the way, because these are damping wings. You get into the radiation damping portion of the curve of growth. It's no longer Doppler broadening. It's a quantum mechanical effect, the uncertainty principle, basically, that kicks photons way out into the wings of the lines. But now you can see the interstellar lines in all of them, and they're labeled along the top. Usually low ions, neutral or first ions of gas, but a few higher ions are seen. That's because the interstellar medium isn't all neutral gas or cold gas. It includes a hotter phase because of the supernova and photoionization from hot stars. Okay, so now I'm going to shift to the IGM-CGM, intergalactic and circumgalactic gas, give you a couple of pedagogical slides and then talk about what COS has done using the benefit of the far ultraviolet. So on the right is the pie diagram from Planck. It's been updated a little bit since 2015. The 2018 data release changed some of these slices a little bit, but not much. We think that about 31% of the universe is gravitating matter. And the other blue slice is dark energy, which we have no idea what it is. We can speculate what dark matter is, but all the usual candidates are getting quickly ruled out by astronomy. But it may be some exotic particle, it may be an axion, it may be something we don't understand about gravity. But the little slice in cyan labeled atoms, I think we understand. We think we know not only what they're made of protons and neutrons and atoms and molecules, but we think we know how many were produced. And I get this question a lot from reporters and science writers. How do we know that it's 4.9%? Isn't that a little bit arrogant? Well, this is first what the deuterium to hydrogen ratio gives us. And more recently, the same number is what the microwave background oscillations give us, the sound waves. And precision cosmology now agrees between D to H, meaning nucleosynthesis in the Big Bang leaves you with a certain amount of deuterium, which suggests 4.9%, and the sound waves in the acoustic peaks of the microwave background give the same number. So I would say within a few percent, we're pretty sure that we know what to go looking for in terms of cosmic baryons. Now, only about 10% of those are in galaxies. And if you add in the halos of galaxies and clusters of galaxies, collapsed phase, you can get that up to about 20%. But where's the rest of it? Well, we think, and COS has been a major part in showing this, we think that 50 to 80% of these baryons are still left out in the IGM or have fallen in a little bit to the halos of galaxies where they mixed with outflowing metals in the circumgalactic medium. So most of the baryons are still out in between the galaxies. That tells us something very fundamental about galaxy formation, I think. It's inefficient and it's still going on. There's still matter falling in. Now these numbers, as I'll show in an upcoming slide, have uncertainties in them. And we're working on knocking down those uncertainties, but they have to do with not knowing the ionization corrections. We have to know the ionizing background, mostly in the EUV, from 1 to 10 Rydbergs. We also have to know the size and structure of the absorbers. We're relying a lot on theoretical work, like the left simulation shows of this cosmic web. And we have to do corrections for ionization and metallicity. So why are these important to me and to many other people? This is a very active and competitive field. Well, first, as I said, it contains a lot of the baryons. This is a source of matter for new star formation, and in particular, low metallicity infall to galaxies. If you're interested in stellar astronomy and the star formation metallicity, there's something called the G dwarf problem, which has to do with why so many stars have the metallicity they do. Low metallicity, lower than the sun. G dwarfs, meaning stars like the sun. Well, one way around that is to bring in a continuous supply of low and intermediate metallicity gas. And then finally, something that's very important to theoretical models of how galaxies form and evolve. This IGM and circumgalactic matter is a fossil record of the feedback from star formation and reionization, which happened in the distant past. So when we say feedback, that's a very broad, glib term. What it means to a galaxy former simulator would be three things, I think: ionizing radiation, kinetic energy, heat, which could be blown out in winds, and also just thermal energy that gets dumped in from, say, the photons. And then finally, chemical feedback, the heavy elements on beyond hydrogen and helium and lithium. So the carbon and oxygen, silicon, iron, etc. All of those, for reasons I talked about earlier, can be detected through your UV lens. So now to some still pedagogy, but comparing what you get with costs and comparing it with the previous workhorse spectrograph, STIS. This is the STIS Shull E140M in green on the bottom, and the costs G130M. And this was a spectrum of a nearby quasar, Parks 0405. And there's a picture of it up there, spread out into this press release picture that we made for the early release. And you can see that in 9.7 kiloseconds on cost, the red spectrum, we got an incredibly good signal noise greater than 50 spectrum. STIS Shull has better resolution, but without the signal to noise to go with it, it's hard to exploit. The STIS spectrum was more than twice the observation time, 27 kiloseconds. So you can see, I can't point with the cursor, but you can see the lines in red. They're all very, very definitely there. The strong line at 1216 angstroms, again, is Lyman alpha, but in its wings, you can see the oxygen 6, one of the oxygen 6 doublets at redshift 0.167. That's an intervening absorber in the intergalactic medium. And there's two lines that go with it. There's another one if you look carefully. And there are others. So let me move to the next slide and zero in on that oxygen 6 doublet. Again, comparing this STIS spectrum on the bottom with the cost spectrum on the top. So STIS definitely detected it. And so some of the original announcements that, hey, we found oxygen 6, hot gas out in the intergalactic medium, came with STIS, and before that with FUSE. But you can see the spectrum is a little bit ratty. But now look at the top spectrum. Not only do you see it, you can see components in velocity. The signal to noise really opens up all kinds of new astronomy you can do. We can also do Lyman beta. There's the Lyman beta that went with the Lyman alpha line. So one of the early things we did was talk about the Lyman beta forest, alpha, beta. We also got some higher lines in the Lyman series. So this is a quasar, a fairly nearby quasar, redshift 0.234. And this absorption system is intervening. It's at lower redshift, so it's in between us and the distant quasar. So the quasar or Seyfert galaxies are just lighthouses that we use to shine through the intervening gas. So back to a little bit of theoretical work on what you might expect to see and what in fact we did see. This is a simulation that Britton Smith and I and some others at Colorado did using the ENSO code. There are many more simulations that are far more sophisticated that have been done since that. But we wanted to just see what the feedback could do to the intervening filaments in the cosmic web. So if you look, you can pretty clearly see the cosmic web, and it's actually broader than just the filaments that you would normally see, and that's because of feedback. And around the galaxies, in yellow, you can see what happens from the outflowing winds. The outflowing winds shock heat the surrounding gas, and there's also infalling shocks from accretion. So the formulae that I put down there are just the standard shock jump conditions, the Rankine-Hugoniot jump conditions that say what the KT energy, the thermal energy behind the shock is for a shock of velocity V sub s. And so for a 200 kilometer a second shock, which is a pretty low velocity shock for a wind, you get gas right at the peak of oxygen 6, 400,000 Kelvin. And V200 is the velocity in units of 200. So you can see that even higher velocity shocks will kick you up to millions of degrees. So the right is a temperature scale, and a lot of the yellow gas in the circumgalactic medium is up at temperatures of 1,000,000 or 2 in yellow. And that is right where helium-like oxygen, O7, and hydrogenic oxygen, O8, have their effectively Lyman alpha or K alpha absorption lines. So if you want to observe the hottest gas, 1 or 2 million Kelvin, just like in the sun's corona, you want to look in the X-ray. But if you look at the red, the feedback along the filaments of the cosmic web, and it turns out also in the circumgalactic medium, the oxygen 6, which is down between 1 times 10 to the 5th and 10 to the 6th Kelvin, 3 or 400,000 Kelvin is the peak. That's right in the UV. It's the 1032, 1038 angstrom doublet. So just to go back, that's these lines here. That's telling us that unless this gas is photoionized, which some of it could be, but we think most of it is collisionally ionized, we've detected gas at just under the virial temperatures of a lot of these galaxies. And so there's a lot of theoretical debate about what makes the oxygen 6, where is it? It's intermediate between photoionized gas and shock heated gas. Maybe it's interfaces in mixing layers, conductive mixing layers, or maybe it's photoionized or shock heated. That's still an open question. So this just summarizes, I annotated a diagram that Joel Bregman made in his annual review article, which was more about X-rays. But I've labeled the 07 and 08 lines that I just talked about in the X-ray. Those are down in the X-ray, 21.6 and 18.97 soft X-ray. And they have been seen with Chandra and XMM, but at low resolution. If you want to get the sensitivity and the high resolution, you want those UV lines, oxygen 6, neon 8, carbon 4, and Lyman alpha, which is still very sensitive. This is a plot showing the sensitivity of the column density for a typical cloud at these temperatures. So back to costs. Costs used all those lines labeled, including neon 8, 770 and 780 angstroms, with a little bit of redshift that shifts into the cost band. Oxygen 6, nitrogen 5, and carbon 4 are right in the middle of the cost band. Okay, so I'm not going to dwell too long on this. This pie diagram is one that Charles Danforth and I put together, and Britton Smith contributed a lot of the simulations that went into it. This is a mixture of the cost observations plus the ionization corrections you need to turn Lyman alpha or oxygen 6 into total baryons. And let me just say a few words about that. If you measure Lyman alpha, the Lyman alpha forest, this bottom in orange, you're measuring the neutral hydrogen. You have to correct that to get the total hydrogen. That's a photoionization correction. So you have to know the radiation field. And then if you look at the blue or magenta on the top left quadrant, oxygen 6 and warm, hot, broad Lyman alpha, those are in hot gas. There you have to, again, make ionization corrections and also metallicity corrections for the amount of oxygen. How many baryons go with the oxygen. So that's where the theoretical work comes in. And this paper back in 2012 describes all that. Over in the bottom right, in green, are the collapsed phases. As I said, galaxies and their halos are something like 10%. If you add in the circumgalactic matter and intercloud medium and clusters, you can get that probably up to 20% in collapsed phase. This little slice labeled just next to the Lyman alpha forest, labeled cold gas, it's in, I guess that's light orange, 1.7%. That's a blind survey of 21 centimeter. Again, not very sensitive. The Lyman alpha is where you want to be to measure the bulk of the Lyman alpha forest. So to sum up what you should take away from this diagram, and not much has changed since then, we've accounted for something like 70% maybe of the missing baryons. Most of them are in between the galaxies or out in the halos of galaxies. About 30% is still missing, and I suspect we will find that. We've started to see hints of it with XMM and Chandra. We'll find that in the X-rays. Okay, so now I'm going to talk a little bit more about the actual data that went into those plots. And this is by no means a full survey of what's been done, but it'll give you a flavor. So this was a paper that Charles Danforth and I and John Stockey wrote early on, 2010. We turned our attention to a blazar, a BL-LAC object called PG 1553 plus 113. It was an unknown redshift at the time. A lot of people in the blazar community told us its redshift had to be no more than 0.2 because of an effect where it should pair produce against the infrared background. So gamma rays should not have gotten through to us. And yet this was a TeV bright blazar. Well, we, to our great amazement, found a Lyman alpha forest. So the spectrum, again with G130M and G160M, shows a Lyman alpha forest of intergalactic absorbers. And we've identified all these lines as hydrogen, neutral hydrogen, all the way out to about 1740 angstroms, where it stops. And so a very careful job, and it's been repeated by others since then, suggests that the redshift of this blazar is 0.43. So whatever pair production that was being done can't have been too severe because these gamma rays got through, and so did a lot of far UV radiation. There were a couple of lines out there that could have been Lyman alpha, but they turn out to be nickel 2. So you have to be a little careful. One of my goals was to really go after Lyman limit systems, LLS for short. These are some of the strongest Lyman alpha absorbers, column densities above 10 to the 17.3. Why that number? That's optical depth 1 at 1 Rydberg. So neutral hydrogen will absorb the Lyman continuum at 13.6 electron volts, or 912 angstroms. And that's what we're seeing here. So these are just two of many absorption systems that we found in our survey. Nick Lehner and another group the very next year found a lot more and did not only that, they had access to the Keck telescope, but they found the metals that go with them. So the Lehner et al. Paper does the metallicity, Chris Hauk and Lehner and others. But we focused on the hydrogen because these absorbers are probably responsible for a lot of the opacity in the Lyman continuum of the intergalactic medium. So here's one at the top, a Lyman limit system. The Lyman limit is labeled in the blue, the cyan. And again, because of the miracle of the redshifting universe, we can see it. This is at redshift 0.4633, and there it is at 1333 angstroms. And all the Lyman lines, higher Lyman lines that go with it. Lyman on beyond alpha, beta, gamma, delta, all the way up to 12, 13, 14, and then converging on the Lyman limit. So we saw almost every one of these up to Lyman 12. And on the bottom is a little bit lower of a column density, a partial Lyman limit system at redshift 0.2823. So again, labeled in blue. This is a lower column density, but we could still see it. In fact, we could see them down to column densities of 10 to the 15th or so, not because of the Lyman edge, which is getting pretty weak here, but because of this Lyman line series. That's a telltale sign when you see this series of absorption lines converging on the Lyman limit. So we learned a lot about how accurately we can measure these column densities. We estimated a model for the intergalactic opacity, how far you could see, and convinced ourselves that even with this kind of opacity, you could see quasars in their rest frame pretty easily, many of them out to redshifts of around 2, and maybe a little bit above for a few of them. Now, one other thing before I leave this line, on the bottom spectrum over here on the right, there's this line, and it looks like Lyman alpha, but it's not at the right wavelength. This is Lyman alpha, I labeled it, and this geocoronal emission at the center. And you can see the red wing of the damping wing of interstellar H1 in Lyman alpha. What's this thing here? Well, we're looking around at a few other lines. We and others, Todd Tripp actually found this first. It's a sub-damped Lyman alpha system in the Virgo cluster. It's a galaxy in the outskirts of the Virgo cluster. And so you can find these things, and we found another, 5 or 6 or so of them, just serendipitously. These are intervening galaxies that have enough hydrogen to absorb in Lyman alpha. These are column densities of 10 to the 19th or so. Okay, now I'm going to talk a little bit about this feedback and outflows and circumgalactic matter. First, the press release cartoon, more pedagogical. Why do we look at this? Why is it important? A good issue to explore if you're a theorist working on simulations of galaxies is the question of, do starburst outflows escape their halos? Do they have escape velocity? Because they have to climb their way out of the potential. So on the left is a galaxy with vigorous star formation that has enough pressure to drive a wind, or maybe it's cosmic rays that drive it, that will flow out to the intergalactic medium. And just to remind you, 1 kilometer a second in a million years flows a parsec. So 100 or 200, in this case, 200 kilometers a second over a gigayear gets you out into the halo, 200 kiloparsecs. So that's certainly circumgalactic medium and getting into the intergalactic. Now, a galaxy like our Milky Way, its salad days are over. Its active days where it was blowing winds that clearly escaped are probably over. There is the Fermi bubble, but the Fermi bubble doesn't have escape velocity, we don't think. So a lot of this gas going up from the disk, from hot stars and supernova, probably turns around and flows back in. Some of it during active phases could get out pretty far, and certainly did in the past, but a lot of this gas has velocity less than escape velocity, and that will recycle and bring heavy elements and metals back in. So what we did with COS and what the COS Halos team, again, I'll just reference Jason Tomlinson and many others on his team. Jessica Work has been a key player in following up on this with the galaxies. They found a lot of galaxies, 44 in particular, that some were active star forming and some weren't so active. And they found, more importantly, the quasars behind them. Now, they had to be bright enough. Typically, you'd like to have 16th magnitude or brighter, 17th in a pinch, to be bright enough to get a good spectrum looking through the outskirts. And typically, it was one galaxy, one quasar. Now, in the future, much bigger telescopes will be able to find many quasars behind these galaxies. I'm looking forward to that. But right now, it's pretty much one to a customer. And they were able to look and find oxygen 6 doublet and many other lines. Let me just quickly get to the main point. What they did by looking at the galaxies and measuring their star formation rates from their colors was derive the star formation rate, or what's called the specific star formation rate, which is just the star formation rate divided by the stellar mass. It has units of 1 over time, obviously. And so a typical number is 10 to the minus 11 per year. If you take the reciprocal of that, the inverse of that, that's basically how long it would take at the current rate to use up the gas from star formation rate. Now, we all know that there's gas falling in and there's more gas being recycled, so it's not that simple, but it's just a good working number of when a galaxy might get quenched, is the jargon, when it might start running out of star formation, running out of gas to keep going. So what they found, and I've annotated their diagram, on the left, the column density of oxygen 6 that was observable was about 10 to the 14, maybe 10 to the 14.3 per square centimeter. And I've put a little red arrow there as a lower limit. And I put another vertical line at 10 to the minus 11. That is a magic number where they started to see oxygen 6 and below which they didn't. A lot of the red symbols are stars that were in their sample. It had quasars behind them, but they were passive. The star formation rate was low, and they didn't detect oxygen 6. Now on the right is a panel that's been popularized by the Sloan survey and many, many others. The jargon I want to go through is the main sequence, or the red sequence along the one sequence, and blue sequence along the other. But let's just stick with the main sequence. These are stars with very high star formation rates, specific star formation rates of 10 to the minus 10, even 10 to the minus 9. And I put on it a plot, I annotated it with the Milky Way. So the Milky Way has a specific star formation rate of about 5 times 10 to the minus 11. And going back to fuse studies, the Milky Way has typical O6 columns of about 10 to the 14.2. So it would put it right there where that purple ellipse is. In the main sequence, it's an active, fairly active galaxy, but I think it's, as I said earlier, its heyday or salad days are over. It's probably getting in the process of getting quenched unless something turns on again, a star forming phase, and replenishes the oxygen 6 in the halo. And the Milky Way, come back in a billion years, it will be in the red sequence where you wouldn't see it. So I had some fun with their data. This is one of my projects back in 2014 when I was in sabbatical in Cambridge, England. I took their data, which they plotted on the left. This is from Tomlinson et al. Cos Halos paper 2013. They spread the galaxies out by putting the galaxy at the center and moving the quasars. So what you're actually plotting here in the squares and diamonds, blue and red, are the location of the quasar in impact parameter. So if I go back to this figure here, the impact parameter is how far off the sight line to the galaxy the quasar target was. So you never hit the bullseye. You came close in a few cases, but typically they found that the active star-forming galaxies, 28 of them, blue squares, were out at 50 or 100. There were a few that went out a little farther, kiloparsecs. So you can see these rings. Now, an astute observer or listener would say, well, how did they know the position angle, where to plot it? It's completely arbitrary, as they say. They just took the position angle on the sky, north-south, and put the quasar down at that position angle relative to the galactic center, galaxy center. So you can see that they've got red diamonds and blue squares all the way out to 150 kiloparsecs. What I wanted to look at was, okay, let's renormalize these distances, these impact parameters, to the virial radii, because their galaxies were all of different sizes and shapes, and the Cos Halos team has gone on and looked at dwarf galaxies as well. I haven't come back and redone it with that, but I did my best to estimate the mass of the galaxy and its virial radius, and so renormalize the impact parameter R in units of the virial radii. And now you see somewhat of a different story. What you see is that the passive galaxies were all within one virial radius, but the active galaxies, the O6, went on beyond the virial radius. And then, I'm not showing it here, but in a paper that John Stocky led, we looked, and Brian Keeney also in a later paper, Stocky and Keeney, 2013, 2014, we looked at the full IgM sample. And it's pretty clear that there's oxygen 6 related to galaxies, but it's been blown, it's gas that's been blown well beyond the virial radius, 5 virial radii, 10 virial radii. So I'm pretty convinced that there were winds in these galaxies that blew the metals well outside the escape velocity radius, the virial radius and escape velocity radius. And this has polluted the intergalactic medium. So now shifting to a little more detail on the intergalactic gas. If this picture is correct, that metals were made in stars, in galaxies, and blown out into the circumgalactic and intergalactic medium, then we should be able to see that. So this is the cost science team's papers. One I did in 2014 and one that Charles Danforth led, which is a major work. I recommend it to everyone interested in the low redshift IgM and its metals. To date, it's the largest survey, 82 sight lines to quasars over total redshift path length of 21, over 2,500 Lyman alpha absorbers, including higher Lyman lines. The metal line systems I've listed there, not as many, almost 300 in oxygen 6. You might say, well, why didn't we see as many oxygen 6? Well, partly it's redshift. You needed enough redshift to shift them into the cost band, but it's also metallicity. You need to have enough column density to see them, something like 10 to the 13th column density of oxygen 6 for us to be able to see them. And so what we looked at in Lyman alpha found all of these weak lines. This plot here shows the power law distribution. Most of the Lyman alpha forest are the low column density absorbers, 10 to the 12th, 10 to the 13th. And it's not till you get up well above where that arrow is, 10 to the 13, 10 to the 13 and a half, that you have enough column density to see them in the metals. So we saw a power law n to the minus 1.65. That agrees very well with what a generation of Caltech and European astronomers have found in the high redshift Lyman alpha forest. And I want to pay tribute to my old friend and colleague Wal Sargent, who did a lot of this pioneering work, and of course Chuck Steidel and others since then. This is the same power law. It's changed just a little bit since high redshift. Now in oxygen 6, it wasn't just the same power law. There was a break, and this is what we found with those 280 absorbers. We found a double power law that broke at about 10 to the 14th column. We should have been able to see them below that, and it's a different slope. So this suggests two populations that we've detected. One, the strong absorbers at high column that we associate with the circumgalactic halos, and then the weaker ones with a lower power law and probably a lower metallicity with the intergalactic medium. Now there's another follow-on paper that Blair Savage did with 54 absorbers over somewhat lower column densities, also with cost. So I note that for completeness. And there's another paper that's just been accepted that I think should be out within the week or two, with Narayanan as the co-author, the lead author, Anand Narayanan, Blair Savage, and others. That's in carbon 4. Okay, so what I have to tell you finally is about something that does hark back to work that Wal Sargent did and Alec Boxenberg did. Of course, Wal Sargent passed away much too soon, but Alec and Wal were working on this project, and I was fortunate enough to be in Cambridge the same year that Boxenberg was putting this final touches on that paper. So I want to highlight that. His work, which came out in 2014 with Keck, shows four triangles, which is the best survey I know in the Lyman alpha forest for the metals, carbon 4 and silicon 4, these purple triangles. And I'm showing it both for carbon 4 on the left and silicon 4 on the right. And then many other papers that have been done with Keck and the VLT in red. And then the cost work at the very low redshift, these blue asterisks. That's our work. There's also work that Stis did, Kathy Cooksey in green that I've labeled there for carbon 4 at slightly higher redshift. She got out into the near ultraviolet, and then also in silicon 4. The green is Cooksey's work. But you can see that the metallicity from redshift 6 and has just been slowly climbing all the way up. The European work, de Odorico et al., is in red in both surveys. You can see that those optical surveys stop at about redshift 1.6. That's because the optical that's where those lines redshift out of the UV into the optical. So there used to be a gap between about redshifts 1.6 and redshift 0. That gap is now filled by the ultraviolet surveys with Hubble, both Cooksey et al. Papers and our papers with Koss. So what I want to leave you with is not only that the metals have increased by about a factor of 10 since high redshift, but the intergalactic surveys that we've done show that quantitatively, the IgM contains about 10% of all the heavy elements formed. So where are the rest? Well, the rest are still in the galaxies and in the circumgalactic medium. They didn't make it out of the potentials, and they're still falling back into the galaxy and helping to form new stars. Another wrinkle that Willie Fowler would appreciate, just to make a Caltech reference, Caltech was involved in a lot of the early nucleosynthesis, Burbage, Fowler, and Hoyle paper, and the so-called alpha nucleosynthesis told us that elements like oxygen and silicon and sulfur should be enhanced by massive stars and supernova explosions. And we found pretty clear abundance ratios that silicon to carbon and oxygen to carbon are enhanced in this gas, which we're pretty sure formed from supernova. In other words, silicon to carbon is supersolar abundant. Okay, now I want to switch to the last topic, which is quasars. Quasars being objects that we can see in the rest frame UV. This is what we saw with low redshift. This is what we saw going to a little bit higher redshift. And we started to see these lines that are in the far UV and extreme ultraviolet. There's the hint of the neon 8 doublet. And finally, just to cut to the chase, we stacked together, co-added, 159 of them. This is a paper that Matt Stevens did for his undergraduate senior thesis at Colorado. Matt just finished his PhD at Texas, and he's now a postdoc, so time flies. What we found was not only the standard lines of carbon-4 and Lyman alpha and oxygen-6 that you see along the right, but these EUV lines and an EUV continuum, which is pretty hard, new to the minus, whoops, sorry about that, new to the minus 1.4 or 1.5, going on down to 450 angstroms. We've been going farther since then, and just a science note, why is it interesting to me? Well, if you do cloudy models of those EUV lines, you find that not only are they hot, broad emission lines of 40,000 Kelvin or more, but they also are extraordinarily high densities, 10 to the 12th, 10 to the 13th or higher, exposed to high fluxes. So this is gas way down near the quasar. And this is where we are today. We've got another 6 quasars. Since then, we're probing the EUV with 140L down to about 425 angstroms. Okay, time is getting short, so let me just finish with a couple of slides on going out to redshifts a little higher than where I thought we could go, redshifts 2. There are a handful, literally, maybe 2 handsful of quasars where you can see down to the helium-2 Lyman alpha line, which is at 304 angstroms. These are the so-called helium-2 quasars. And so Koss looked at 3 of them, the Koss science team, some others, including Gabor Warsak and Jason Prochaska and others have been looking at a number of others. These are ways of probing the helium reionization era, which was probably about 11 billion years ago, back at redshift 2.7 or 3. So let me just show you the data. This is one of the ones that Fuse looked at and Stis looked at and Koss looked at with COS, we were able to see the proximity effect of all of this transmission. So the quasar redshift at 304 angstroms is shown in a dotted line. It should have been black, no transmission, short rid of that, but there was a lot of emission because the quasar was bright enough to ionize the helium. And then there's a few other places where quasars transverse to the sightline burned off helium-2 regions, helium-3 regions around it, and made transmission flux. Here's the one, it was my favorite that we wrote several papers on over the years. 2010 was the COS paper. And you can see there's a proximity zone, maybe due to a couple of transmission windows, but mostly near the quasar, it's pretty black. And then there are these long troughs of helium-2 absorption. So this is showing the patchy reionization epoch, which started probably at redshifts 4, but didn't really kick in till redshifts around 3. And by redshift 2.7, the redshifts are along the top. These ionizations of helium overlapped. So I'm going to wrap up in just a few slides. Enjoy Hubble and COS and Wide Field Camera while they last. I hope they last. The Hubble is still going strong. The next major mission in the UV, optical, and infrared, near infrared, may not be until after 2035 if you want to wait for a flagship. And LUVAR is the one being studied. In October, we'll hear from the decadal survey whether anything like this is in the cards. But there are other opportunities. There are still SMECS and mid-X explorers in the 150 to 240 million range, something that I advocate a lot. Probes, you can do a lot at the $1 billion range, as many missions like FUSE and WMAP have shown. $1 billion doesn't buy you as much as it used to, but you can do an awful lot of science. And then something that the people at Colorado and around the world are learning, CubeSats. So I'm looking forward to seeing what is possible within the budget. I don't have time to talk about it, but this was a slide that I pulled out of a 2009 talk, looking forward just before the COS launch, looking forward to what we wanted to look at in the far UV. And it pretty much is the LUVAR science mission, both in imaging and in absorption spectroscopy. With that, I will close and be glad to take questions.
Thanks, Mike. A very comprehensive overview of what COS has done. I think I've been trying to absorb it. Fortunately, we have recorded the talk. The slides are up for those like me who will probably do a pass too. Questions, Wenbin Lu.
I have a question on the correction. Let's say if you see some absorption, let's say H1, you have some H1, and then you use that to correct for the ionization fraction to get the CGM contribution to the total baryons. Not to do with the kind of the ionization fraction. I want to know what kind of the, in one slide you show the azimuths, you say the angles are randomly put. What kind of inhomogeneity there is in the azimuth direction, right? If you let's say for each halo, you only have one this quasar line of sight.
Right.
Do you actually infer that the entire 2 pi has the same column density, and you assume maybe that entire 4 pi is the same?
Well, first I should clarify that the work that I showed here was entirely by Jason Tomlinson and his COS Halos team, but they did the same kind of corrections that we did. Yes, because they only had one line of sight through the halo, they had to make some pretty bold assumptions. First about metallicity and also about ionization. Since then, they've looked a lot at, by imaging the galaxies, they've looked at inclination to the major axis and minor axis. So they've come a long way since then, but they still suffer from having only one. I think in maybe 2 cases they had 2 sight lines, but typically one quasar sight line. So that's certainly an uncertainty in the issue. The gas
is there a bias? Let's say you only see those ones where the line of sight going through some higher column density in particular.
Well, there's an observational bias that in order to see the oxygen 6, you need enough column density, typically 10 to the 14.3 per square centimeter, maybe 10 to the 14 if you really observe hard. That's not the issue. I think the issue is ionization corrections. The gas gets too hot. Remember, the oxygen 6 very quickly gets turned into oxygen 7 and oxygen 8 at 1,000,000 degrees. So if you come out at a high velocity wind, probably you need the X-ray spectroscopy to see it. So that's a key science project for the next generation of X-ray telescopes and UV telescopes.
Yeah. Thanks so much.
So once you asked your questions and you're happy to lower your hand. Yeah, thanks. While others are mulling through, I have a question. You said something like the earliest the next UV mission is, mid-30s, which is kind of long ways now, it seems. Now, Hubble, of course, is like the big, is the only UV instrument for certainly spectroscopy. What are the issues apart from Hubble? Let's say Hubble continues to work with a no gyro, all that sort of problems is not what I'm talking about. What are the issues with the course itself? That is there like a time-dependent performance, or I don't know, some consumer? I have no idea. Some things what are the limitations of course itself operating 10 years?
Well, let me go back one step to your first point. Satellites usually end their life by lack of fuel.
Okay.
To control it, or from power supplies, a power supply fails, or a gyro fails.
Okay.
Sometimes if you're in the infrared, you run out of cryogen. But in the UV, Hubble has enough fuel to keep operating for quite some time. They replace the batteries and power supplies. So in principle, it should last. The power supplies are an issue. You never can tell when they fail. That's what happened to STIS. That's what happened to one of the spectrographs on Hubble. So you can't predict that. But most people that have looked into the likelihood have said it could last another 5 years. But it could fail any day. Now, to your point that we have to wait till 2035 or whatever. That's only if you have to have something that is a flagship class that would take 10, 15 years to build. And if you're not first in line with the decadal survey, it could take some time. There are 4 flagships. 2 of them have UV capability, HAB-X to look for extrasolar planets, and LUVOIR. One is X-ray and one is far infrared submillimeter. So we'll see. But I'm hoping that the decadal committee, and I'm not on it, so I have no private knowledge, I'm hoping that they will also recommend that NASA run a probe line. And that could happen sooner. There's also a Russian-German telescope that's in the planning. I'm hoping, I'm not in on that. I hope that helps. And there's CubeSats and rockets. You don't get as much time on a rocket, 5-6 minutes perhaps above the Earth's atmosphere, but you can UV qualify and test out new technology, including coatings, detector coatings and mirror coatings. And CubeSats, you can get a lot more time. And there are several of them that are already flying or will fly soon. There's one at Colorado that Kevin France has, and there's some others.
Yeah. So what about the cost itself? Some of these UV detectors.
Oh, sorry. Yes. Yeah, I meant to say the UV detectors slowly degrade. There's background. The count rate used to be essentially 0. The dark count, we call it. It slowly is increasing. You can read about that online, the Space Telescope Science Institute website. There's also places on the detector that get burned in. So you can move the spectrum around to a different position. They've done that a number of times. So that keeps it updated. The exposure time calculators are kept up to date, so you can see what it would take if you propose, well, I guess it'll be cycle 30. If you propose in cycle 30, per Hubble, you can see what it would take. That's wavelength dependent. All these statements are wavelength dependent. There's also the choice of STIS. And so if you want near UV, it's often a choice between the using the COS detectors, which are sensitive, but less efficient because of their wavelength coverage. You have to do 3 of them if you want the full coverage, versus STIS, where you can get it all at once. So many people choose to use the STIS and UV. Unfortunately, they're both available.
Okay. Other questions? Okay. I had a question which was for especially the low redshift universe, where you said you're looking at a quasar at some high redshift, 0.2, I mean, not high,
Yeah.
but
Oh,
and
there's
then
one.
you found a thing in Virgo cluster accidentally.
Oh, that one. Yes. Let me go back
Yes.
to that one. Yeah, there are actually a lot of.
So was that a
Whoops, I went by it.
surprise? I mean, is that a surprise if you just, so the question I had is, if I choose randomly some quasar, I don't know, it's far away, sufficiently far away,
Yes.
what is the probability I'll find something in redshift less than 0.1?
Well, it depends on the column density. So let me
I mean,
just,
sorry, in damped lamina, like
yeah,
I want,
let me, for the benefit of the rest of your listeners, it's all Lyman alpha, but they come in different flavors. The Lyman alpha forest, by definition, are the low column density, below about 10 to the 16th. The Lyman alpha systems, Lyman limit systems, technically 10 to the 17th, 0.3, anything with a Lyman limit, but they're rare. The number per unit redshift of a Lyman limit system at low redshift might be only 0.3, 0.5 at most. So you've got a pretty good chance of not getting clobbered by one of them. If you go to the damped Lyman alpha, which are 10 to the 20, 10 to the 20.2, those are really rare. And so this was a surprise. I mean, it didn't take me long to figure out, oh, it's got to be Lyman alpha. Let's go look for the other lines. But that Lyman alpha through the Virgo cluster would be, that would clobber a lot of your Lyman alpha. Now look here at this spectrum on the top. This is a Lyman limit system. This is what happens to it short root of 1,340 angstroms. It's black. Okay, so if you were going after oxygen 6 in the Milky Way, or molecular hydrogen, or something in the far UV, you would see nothing. But the good news is, as I said, these Lyman limit systems, even if you don't know they're there, they're pretty rare. The other thing I'll say is that you can test for them other ways, and the classic way is look for magnesium-2, which is a 2,800 angstrom doublet. Just a little bit of redshift gets that into the optical. And so you can do a magnesium-2 survey at redshifts of 0.1, 0.2, 0.3. And if you see a strong mag2 system, odds are pretty good you'll see a Lyman limit system or a partial Lyman limit. And that's a way of making it a little bit less blind, but saving you some grief, if that makes sense.
those in itself are not interesting. I mean, this Virgo
Oh, they
cluster.
are. I mean, there's a whole group of people who love Lyman limit systems and magnesium-2 systems and the galaxies they live in. I'm just saying, if you want to do other things that require far UV photons, you know, the Lyman limit system is the poison for your meat.
Okay.
If you know the quote.
Okay. Any other last chance for anyone now? Not.
I may have spoiled them with the fire hose effect.
Okay. Then let me ask the last question also.
Oh, I have a question.
Yeah.
I have a
Who's that?
question.
Hey, it's Chris
That's
Martin.
Chris. Sorry. Hey, Mike, how are you doing?
Good to see you.
Nice to see you.
Maybe I'll see you this
Wonderful
fall.
talk. That would be great. The hyalinization lines that you think might be associated with virial shocks in filaments, Is there any other evidence, and is there any kinematic evidence about that?
Yes. Let me try to find, I'll just leave that up. The issue is, are these lines of neon 8 and oxygen 6 collisionally ionized or photoionized? And what you find looking into it a little bit more deeply is that, yeah, you can make oxygen 6 photoionized, and even with heroic efforts, a little bit of neon 8, if you get it low enough density. And it's because it's the ratio of photons to density that matter if you're photoionized, the so-called photoionization parameter U. But if you measure U or infer U from other means, you find that in most of the cases, it's not sufficient. So I would say, this is a theoretical statement, I would say that in the far extents of these halos, you could have photoionized O6 and neon 8, but if you go in closer, within 100 kiloparsecs, certainly within 50 kiloparsecs, it's hot gas. And that raises a whole other set of issues. Where is it spatially? Something, I had occasion to be looking back at your old 1990 paper with Stu on the O6 emission and carbon 4 emission. Where is it? Is it interfaces? Is it patchy? Yeah, I think that's still an open question.
So there's like another minute to spare. So I'll put in this question. There's a growing, I don't know about growing. There's been statements being made that the circumgalactic medium of our galaxy has a dispersion measure of 30 centimeter minus 3 parsecs. Okay, that is in addition to the 23, which we see vertically up, okay?
Yes.
Which suggests, a large amount of the IgM is not IgM as in homogeneous, but really kind of, these galaxies are very fat in their CGM. Do you buy into that?
Well, yes. In fact, if you remember that paper that I asked you in Vikram about, I wrote a paper, I can't remember the year, a couple of years ago, on fast radio bursts and being part of it being intergalactic medium. And many other people are now saying the same thing.
Oh, okay.
Okay,
Well, I didn't realize that.
If you go back and look in there, I actually estimated from the pulsar dispersion measures of Cordes and Taylor and from the oxygen 6 and oxygen 7 that a typical halo would have dispersion measure of, I think I said 30.
Oh, okay.
To the
Well,
minus
I'd forgotten you were the originator of this rumor then, or this.
I'm one of them, but I'm not the only one.
Okay. Well,
Prochaska and many others, Marquardt and their papers have done the same thing.
Okay, then last thing I had, and then really we'll wind up. Okay, you talked of the alpha abundance and how therefore it ties the pollution in the IgM to, basically core collapse supernovae.
Or at least our process, alpha process.
Yeah, alpha process. Okay.
Alpha process.
Yeah. What about iron? No one talks about iron in the IgM. Why is that?
Oh, that's not true.
Yeah, you didn't talk about iron in IgM.
Well, I didn't have time today, but certainly we talk about it and we see it. And of course, it's all over the interstellar medium, and it's produced both in alpha process and in white dwarf explosion, supernova 1As. I just didn't have time to talk about it. It's also very important if you want to subtract off in quasars the iron 2 emission. It's all over the place. So iron is very important. It's there's some very strong lines in the far UV, and you can get excellent column densities.
So the question I had is there? Can you say something about type 1A supernovae actually contributing to pollution of IgM?
I would love to be able to do that, but I haven't done it. It's a little harder. Iron is less abundant than carbon by about a factor of 10. And if you deplete it into dust grains, then it's really hard to find. But I think out in intergalactic space, you can find it. At high redshift, the quasar absorption lines, that's a whole different talk that you could get from Chuck Steidel or some of his students. It's quite important. And it's seen in the highest column density systems, damp Lyman alphas. So iron and nickel and all those iron group are looked at extensively in the high redshift damped Lyman alphas. I'd love to be able to do it in the low redshift medium. It would have to be the higher column density absorbers, Lyman limit systems, partial Lyman limit systems, 10 to the 16th column and above.
Okay, I think we can now wind up this class. Mike, thanks again. Hopefully people will be inspired by your talk and will start writing cost proposals for the next round.
They should.
Yeah, because it's a limited time offer right now, as I understand.
Well, there's a UV initiative. Supposedly they give some slight preference to UV.
Oh, okay.
I think it's only slight.
Okay. Oh, you mean you get a handicap if you put a UV proposal? Okay, great. Maybe
Thanks.
I'll write one myself because I never tend to win proposals, so the handicap might help. So.
Well, it's 1 in 8 odds, so it's tough anyway.
Okay. Bye, everyone.
Thank you.
All right. Bye all. Next meeting is Friday.